Okay, we're back talking about exponential applications, and in particular, this time we're talking about compound interest. And here's the formula that we use for compound interest. This is function notation over here, a of t, the amount after time t, where t is our variable, okay? A of t equals p times the quantity 1 plus r over n to the nt power, where what are all these things? Again, A is the amount after time t. If you're talking about dollars, it's dollars, pounds, it's pounds, whatever unit you're using for money. T is time, and we're going to say it's time in years. P is the principal. Principal is the amount that you put in initially, and R is the annual percentage rate, often abbreviated as APR, and N is the number of compounding periods. So if it's compounded quarterly, then it's 4 periods a year. If it's compounded, I think they call it semi-annually, then it's twice a year. Biannually would make sense also. If it's just once a year, then it's a 1. So let's go from there with this example and see how compound interest might work. The interesting thing is the exponent in compound interest. Okay, this is what blows things up or brings them way down. So let's take a look. Suppose we invest $1,000 at 5% APR. What will the account balance be after 10 years? What will it be after 100 years? Okay, so let's just start with A. Here, I want to use a different color. How about we'll go with pink on this one. Okay. So I don't know the amount. That's what we're trying to find out after 10 years. And I didn't give a compounding period, so let's just say it's compounded annually if it's not shown there. Okay. Compounded annually, which means n is equal to 1. Okay. All right. So we'll plug it into the formula. I'm not going to write the t here, just to let you know. T is the variable, that's why I wrote it in the first place. So A is equal to our principal, $1,000, times 1 plus the rate divided by the compounding period. And we're going to use that rate as a percent. Okay. Times NT, and in this case we're looking at 10 years. Now, again, you're not seeing the n because it's 1. Dividing by 1 just gives the rate. Multiplying by 1 just gives the time here. And something to keep in mind is that rate and time unit stuff should match up. So this is annual and this is annual, okay? All right, so let me just go from here. This is 1,000 times 1.05 to the 10th power, and I'm going to go ahead and just put that in my calculator all at once, times 1.05 to the 10th power, and I get about, I'm just going to round it to the nearest dollar here, 1628.89. Okay. Oh, I said nearest dollar. I didn't, nearest cent there is what I meant. Okay. So how much did we get on our investment there in 10 years? $628.89. That's okay, I guess. Let's see what happens after 100 years. Now, this is interesting. You guys should keep this in mind with your own financial applications. 5%, there are things that offer 5%, certainly not a savings account. It would have to be some kind of CD maybe, and even then you probably can't get 5%. So you're going to have to look at mutual funds or something that gives you a little bit more than that. And that was $1,000 for a lot of people. That's a lot of money to put in initially. So anyway, let me move on. Let's see what happens after 10 or up to 100 years. And what is your guess? Notice that 10 years times 10 is 100 years. So should this be times 10? Should we get 16,288.90? Well, let's find out. I don't think so, but let's see. Okay, here's our original $1,000. Again, it all looks the same in the beginning, except we've got 100 years instead of 10 years. Boy, that's interesting. I guess you're leaving that for your relatives then, huh? 1.05 times 100. I'm going to go ahead and pop that in the old machine to the 100th power. And I get about 131,501. 501 point, round it to the nearest cent, 26. Okay. Interesting. 10 years times 10 is 100 years. The amount times 10 is only 16,000, roughly. But notice that actually, when interest is compounded, we're up to 131,000, way more than 16,000. So that's interesting. That's the beauty of compound interest. It follows that exponential form that we were talking about earlier, where you've got this number here as something greater than 1 and some initial value. What does it look like? Well, the functional form looks something like this. And it gets very steep very fast as those numbers continue on. So keep that in mind. Let me pause for now. I'll do another application, another example of this compound interest stuff on the next video. Stay tuned.